Computer program. Okay, I'm recording.
Okay, I got it. Yeah, well, thank you also for introducing us here. And yeah, as I said, as Wilson said, it will be about heat equations on Mumford curves. And part one will explain what Mumford curves are and how they're related to reductions. The reductions will lead to objects that are graphs, and they can be used to construct heat equations using an idea by Wilson. First of all, the contents. I'll give an introduction, some notation. Aphenoid algebras are the building blocks in order to construct rigid analytic spaces, which are Mumford curves are such in the p-adic case, and or in the local field case, and these aphenoid algebras are analogous to affine algebras. So you can you can pretend you're doing algebraic geometry, and stable reduction of curves is a theorem that is useful in this context. And then I'll come to Mumford curves and their reductions. In the end, one reference for today. So Mumford curves can be seen as the non-Archimedean analogues of closed Riemann surfaces, so surfaces without holes, topologically speaking, and they are used in p-adic string theory by Zabrodin and his colleagues. That was in the end of the 80s, early 90s, in order to calculate higher genus string amplitudes in this context. I will not go into the details of this today, but the Mumford curves have a nice graph theoretical characterization, as I just said in the very beginning. And these are examples of rigid analytic spaces, which are a kind of an analytic version of algebraic geometric objects. They're intimately related to quotients of the Briat-Titz tree, which we have seen in the last session, and this will play a role in our constructions. So first of all, some notation now. K will be a fixed non-Archimedean local field. We will be more general than just p-adic cases because sometimes you will have to extend, well, not in our case, but we'll just fix it. But you have to keep in mind that if you have a Mumford curve, then given by some equations, you will have to extend the field finitely in order to have actual points on the curve, or you have a Mumford curve in the first place. So, and K star or K times is this multiplicative group. We'll put an index K to the valuation or absolute value of it, and OK will be denoting the unit ball. This is a ring, a local ring. Pi is the uniformizer of K, which plays the role of P in the p-adic case. And the absolute value is then, if it's a finite extension of QP, you can think of it as this E that you see here. You take the ETH root of P over minus 1 as the absolute value of that pi. And E, you can think of it as the ramification index, which it is in the p-adic setting if you have a finite field extension of QP. And F is the partner, so to say, in the number theoretic setting, which is the degree of the extension field of the residue, the field extension of the residue field. So the residue field is just OK modulo pi OK. Pi OK is the maximal ideal of the ring OK. And the residue field will be denoted by a small k. And we will need the Briat-Titz tree for it's a tree for the group of Mobius transformations on K. And it's slightly general than we had last time. We just had the p-adic version, but for any K, local field K, a non-Archimedean local field K, you have this thing. And the vertices correspond to disks, either finite disks or bounded disks or unbounded disks centered in infinity on the projective line. We have seen this, I think, on the last session on a slide, where A is a center and R is a value. Now we come to aphenoid algebras. The first important example and the most important example is the Tate algebra. Then we have a theorem called Weierstrass preparation and division, and important consequences of this. And then this allows to construct aphenoid spaces. I'll just give an overview of this. So, but in order to define an aphenoid algebra, we need a general definition of Banach space in the non-Archimedean setting. So we have a vector space over K. We have a norm with the usual axioms, except that the triangle inequality here, 3, is of course the strict with the maximum instead of the sum. And if it's complete, then you call it a Banach space. And then a Banach algebra is just a commutative K algebra with identity and a norm such that you have a Banach space, and the norm of the identity element is 1, and you have this inequality with products. The norm of the product is smaller than the product of the norms, smaller or equal. So now we come to our most important example, the Tate algebra, or also standard Tate algebra. It is a ring of power series, namely convergent power series, by saying that you have coefficients and variables, n variables, and the coefficients tend to 0 with respect to the p-adic norm, and you have with your multi-index alpha 1 to alpha n. And this is a Banach algebra, and it has a norm, the Gauss norm, which is just the maximum norm, or the supremum norm, as you could call it. It's the maximum of the coefficients of the norm of the coefficients in the p-adic value, pi-adic valuation. And again, you have a ring structure on the unit ball and an ideal given by the open unit ball, and you can take the quotient again. In this case, you will get something which is just isomorphic to the polynomial ring in n variables with coefficients in the residue field. So here you see formal convergent power series reducing to polynomials. So you have an analysis connection connected to algebraic geometry over the residue field. And this will be the starting point of rigid analytic geometry. First of all, we need to extend this by saying what is an A module. So A is a Banach algebra, okay, and then a Banach module. M is an A module, which is a Banach module given by a norm. And what you require is that M is, of course, a Banach space with respect to this norm, and you have this inequality A module algebra element times module element. The norm of that is smaller or equal to the product of the norm of A times norm of M, where it did not distinguish between the norms of algebra elements and module elements, but there's a compatibility anyway given by this. And now we come to an aphenoid algebra, which generalizes the Tate algebras. Namely, you have a K algebra for which there is a K algebra homomorphism from some standard Tate algebra to A, such that A becomes in this way a finitely generated Tn module. Now, Weierstrass preparation and division, what you always have is the reduction map on Tate algebras, also later on aphenoid algebras, but remember this is T0 modulo T00, the unit ball modulo the open unit ball, and so an element F gets mapped to this is supposed to be T0, to F bar, and an element with norm F can be mapped to some polynomial in n variables F bar, and an element is similar, is regular with respect to Zn in norm F equal 1 of degree D if its reduction is of the form, it's a polynomial in Zn of degree D. Here you can see that it looks like a polynomial, but the coefficients here, lambda is an invertible element of the residue field, but the coefficients here of the other variables of lower power than D are polynomials in the other variable z1 to zn minus 1. So these are special elements that the Tate algebra has, and these are important. And we will give a notation. We'll call Tn minus 1 the subalgebra of Tn given by the first n minus 1 variables. And here's a theorem, Weierstrass preparation and division. So first, division. If you have such an element in Tn which is regular in Zn of degree d, and you have any element g of Tn, then you can do something which is division with remainder. Namely, you have a unique element r, the remainder, which is a polynomial in Zn with coefficients in Tn minus 1, as we've seen before, of degree smaller than d in the variable Zn, and q an element of Tn. And you have this expression g equals qf plus r. So quotient times f plus the remainder r. And moreover, the norm of g is just the maximum of the norms of the quotient and the remainder. This is almost nice because you have division with the remainder. You can think of something like, is there something like a Euclidean algorithm? Or yeah, it has consequences for the structure of the algebra. But the problem is not all elements allow this, but preparation says that if you have an element of norm 1, then there exists a K-algebra automorphism of the algebra such that the transformed function is regular in Zn of this degree that you have. So you can always transform an element by an automorphism into this situation. And this is good enough for this theorem, namely, first consequence is any Aphenoid algebra. So this Tn has also consequences not just for Tn, but for any Aphenoid algebra. Any Aphenoid algebra is Noetherian. If you don't know what it is, it doesn't matter. It just means that it's nice enough that you can pretend these are polynomials, but just with infinitely many coefficients, non-zero. So Tn is a unique factorization domain. This is an immediate consequence of Weierstrass of Krull dimension n. And another consequence is all norms on an Aphenoid algebra A, which make it into a Banach algebra, are equivalent. So it's also important that you don't have to take so much care of the norm. And every ideal of an Aphenoid algebra is closed. This is also a nice result. And furthermore, any Aphenoid algebra is of the form Tate module.
A quick question. Close.
Yeah.
What topology are we using here?
You can use the norm topology.
The norm topology.
Norms are equivalent.
Okay.
Yes.
Yeah. Thank you.
So Tate algebra modulo I gives you any Aphenoid algebra, and being closed ideal in Tn, you get a Gauss norm on A, and it's again a Banach algebra. So you don't know which norm you want to pick. Well, just take the Gauss norm from Tn, and then you get a norm on A for free. And another result is for an Aphenoid algebra, you can go the other way. There exists an integer d and an injective finite more. So it's a finite extension of such a Tate algebra. And then this gives you the Krull dimension of A, namely d. And another result at the end, which is important for what we are doing, for any maximal ideal M in Tn, the field, so the quotient if by a maximal ideal is, as you know, a field, but this field is a finite extension of the field K, capital K, that we started with. And these are the building blocks in order to build spaces. Like I don't know if you had algebraic geometry, but from there, in algebraic geometry, you make rings or algebras into spaces by considering them as points. There are two versions, the maximal ideals or the prime ideals. So we'll just take the easy version with maximal ideals. So here, the space of Tn, you can view it just as the points with coordinates in the algebraic closure of K of the hypercube. So this is, or the unit, you can say it's a unit ball because it's the maximum norm, maximum of the individual coefficient norms or the maximum norm on K algebra. so the maximal ideas of the residue field then correspond to the affine space AM with coefficient coordinates in K, the algebraic closure of the residue field. And what you have is a surjective reduction map between the aphenoid world, space Tn, and the affine world, algebraic geometry world over the residue field, max Tn bar. I will explain this reduction map a little bit later. But first of all, we want to generalize this concept to aphenoid algebras. In order to do that, well, first we define the space. The space of an algebraic aphenoid algebra is the set of all maximal ideals in A. Remember, if M is a maximal ideal, then A modulo M is a finite field extension of K. And you can say the K rational points are those maximal ideals for which, well, there's the field extension degree is just one. So A modulo M is isomorphic to K. This is the set of K rational points of X. We will use later on in next week, we will just fix K and consider K rational points of these algebraic or analytic objects. Aphenoid spaces. Here are the spaces. So you have an aphenoid algebra and take a point, a maximal ideal, point of SPA, and an element F in A. This is what you usually do in algebraic geometry. You consider such an element of a ring or an algebra as a function. And the points are the maximal ideals. Well, you take the image of F in A modulo X. That's the value. So in general, you could have the range could be different kinds of field depending on X. But of course, if you fix only to a certain type of ideals, then you have the fixed extension field, and then you have a function into the field. Or you take the algebraic closure, then you always have a function from a point into the algebraic closure. So A modulo X is a finite extension of K, and we know that the absolute value of K extends uniquely to an absolute value on A modulo X, and then you can define just the supremum. I was tempted to say norm, but it's a semi-norm in general. But the supremum of those norms of those values at X for fixed F is this so-called spectral semi-norm. It satisfies the axioms of a semi-norm, and it is a norm for special algebras, namely if the Jacobson radical is 0, so the intersection of our maximal ideals is 0. These are nice spaces then. And if you have an aphenoid algebra, then you can since you have this semi-norm, you can do the same construction as with the standard Tate algebra. Namely, the unit ball, it's an OK algebra, and the OA00, the open unit ball, with respect to the spectral semi-norm, is an ideal of A0, and then you can take the quotient, you get a K algebra where small k, residue field. And then you can construct this general natural reduction map from the aphenoid space to the algebraic maximal ideal space of A bar. Namely, you consider such a point at SPA. This is a maximal ideal of A, and this is always the kernel, because A modulo X is a field. So you have a kernel of a surjective K algebra, not field, algebra. So the kernel of a surjective K algebra homomorphism into a field, a finite extension field of K. What you then do is, just as before, you extend the norm, the absolute value of K, uniquely to L, and you view L as an aphenoid algebra over K. Then you can do this reduction thing again, so you can reduce the map phi that you had here, to the algebraic object, and you look at the image of X in the max space of A bar, and that's the image of the map red, reduction map. And the theorem is that this reduction map is always surjective. Let's come to an example. you all know that this here is a disk. Centered in here is a fixed point A, which is chosen as the center of the disk. But this is the set of k rational points of an aphenoid space. And the algebra corresponding to the space is just this algebra. It looks like a Tate algebra, but you have a variable transformation, x minus a over r, where r appears here in the radius. If you do this transformation and take this algebra, then you have SPA is actually the space whose k rational points is given by this disk. So if you want to have more points, you just extend the field. You take the same algebra and just extend the field, then you get more points in that space. Another example, the annulus, where we have here pi is the uniformizer, and you know that between absolute value of pi and 1, there is nothing. So if you take strict inequalities here, then you have this one here, it's down below. This is empty, but not in the algebraic closure. There are points, but no k rational points. But that will be important later. So that's why because in order to have points, I just wrote k alg for this annulus, and this corresponds to the algebra. This is the space of the algebra given by, here you need two variables, pi over x, because you have two inequalities, and you can write this, but these variables are dependent. You have pi over x and x. So if you have two different symbols, s and t, you have a relation between, namely, you have to mod out st minus pi, the ideal generated by this function. And if you reduce this algebra in order to calculate the reduction of this y, this space y, what you see is pi becomes 0. This is like modulo pi, what you're doing in this reduction business. And then you have the algebra small k, st, modulo s times t, because pi became 0. What is this? That means st equals 0. That is, you have a cross, and two coordinate axes intersecting in one ordinary double point. So the reduction of y is the union of two affine lines intersecting in one ordinary double point, called as PD. And what is an important result is that the inverse image of the reduction map of this double point is just an open annulus. And in this special case of this annulus y, we have that, which you should remember, it is empty if you just take the k rational points of this annulus, or inverse image of double point. So example continued, I wrote it down. Y of k, the k rational points of this annulus y is covered by two disjoint circles. Here they are. Take absolute value of x equals pi is one circle, and absolute value equals 1 is another circle, and in between is empty space. They're disjoint, those two circles. It's a covering of this space of k rational points of y. It's not a covering of the aphenoid space, right? You have stuff in between because you have algebraic closure. But remember this in part 2 next week. Now we come to another concept, stable reduction of curves. So we're introducing algebraic geometry now. We have a projective algebraic curve, this time over the residue field, and it has singularities. Its arithmetic genus is G at least 2, and it's called stable if it's reduced. Okay, this is a nice condition. And the only singularities in X are ordinary double points. Just remember that annulus that we had, the reduction was a curve. It's not projective, fine, but ordinary double points, that's mild singularities, no complicated things. And each irreducible component, so for the definition of stable curve, each irreducible component of X which is isomorphic to a projective line, has at least 3 double points of X. So the other components can have any genus and intersect somehow in other component, but if you have a rational curve, then it has to have at least 3 double points. That makes it stable. If that is not, this third condition is not satisfied, then you just call it semi-stable. Here are the stable curves of genus 2 over the algebraic closure of the residue field. There are 7 types of them. The first one is just, well, here's a non-singular irreducible curve, genus 2. The number here is the genus of the components, the irreducible components. Here you have 2 curves of each of genus 1 intersecting in one ordinary double point, or the third one, genus 1 curve intersecting itself in one point, or a genus 0 curve intersecting itself in 2 points, and so on. You have you can mix the genera of the curves. As long as the arithmetic genus is always 2, that means if you sum up all those numbers and the loops or holes that you see, it has to add up to 2. Now we define an absolutely irreducible smooth projected curve. Absolutely means if you look at it over the algebraic closure of the field K of genus G at least 2. And you can define a stable model for X if you have a stable curve over the local ring OK. And the generic fiber is called if you take the tensor product or the fiber product with K, with a capital K, if that generic fiber is isomorphic to a given curve X, I should have taken a different symbol for this stable model of X. But in the special fiber with the small residue field is called the stable reduction of X. So the stable curve is over the residue field, the singular curve, and over the big field K, the so-called generic fiber, you have an irreducible, smooth curve. And the stable reduction theorem says that such a model always exists if you extend the field large enough by a finite Galois extension. So any 2 stable models of such an irreducible smooth projected curve are isomorphic, and there exists a finite Galois extension L of K such that tensoring with L has a stable model. So you can, if you extend the field large enough, then you have nice things, nice curves, nice descriptions of the curve. And Mumford curves go into this. We'll look at Mumford curves and their reductions. First, an intro into Mumford curves, and we'll learn a little bit more rigid analytic geometry on the way. Mumford curves, found by Mumford, they generalize Tate elliptic curves to higher genus. Tate was the first one who did uniformization with the p-adics and examined elliptic curves, and some are named after him. They're genus 1 curves. And there's a 1-to-1 correspondence between Schottky groups, I'll explain this in a minute, in the group of Mobius transformations of K, corresponding to certain, namely the Mumford curves, projective algebraic curves over our field K. So we need more definitions, namely a Schottky group has to be defined. This is a discrete subgroup of the group of Mobius transformations, which is freely generated, so it's a free group, by finitely many, namely G, at least 1 hyperbolic Mobius transformations. So a hyperbolic transformation is one such that the absolute value of the trace squared over the determinant is greater than 1, or if you represent your Mobius transformation by an SL2 matrix, a matrix of determinant 1, you just say that the trace has absolute value greater than 1. What you need is a limit point. A limit point of the group gamma is a point in the projective line, in the k rational point of the projective line, such that there's another one, and a sequence of group elements such that these group elements transport x0 to closer and closer to x. And you say L of gamma is the set of limit points of the group gamma. And a Schottky group has the property that not all projective line points are limit points. So there exist points which are not limit points, in the projective line, actually this is an open condition. So your space omega is quite big. The space L of gamma is then quite small. And the theorem by Mumford is if you have a Schottky group with G at least one generators, then you can take the quotient omega, so the non-limit points in the projective line, which are also called regular points, so the space of regular points, modulo gamma acts on this space omega, and the quotient gives you a projective algebraic curve over K of genus G, the number of generators. So this is an important theorem which shows you that Mumford curves will show you that the rigid analytic spaces. But anyway, this quotient is called a Mumford curve. In order to describe them as a rigid analytic space, we need rational aphenoid domains, namely rational meaning that they're in the projective line, and that's just a hold disk. It's actually an aphenoid space, so we're considering the aphenoid space part and the points. If you take k-rational points, you can think of inequalities with which describe a disk where some other disks are removed from. And the theorem is any Mumford curve has a finite covering by rational aphenoid domains, whole disks, and these domains are glued together along boundary components, namely circles. And in order to see this as a rigid analytic spaces are obtained by gluing aphenoid spaces. So, we need to look at whole disks. So the reduction of a whole disk, a disk with holes, is a singular affine curve x bar. You remember that we had a whole disk, namely an annulus. You have two components. If you have more components, then you can have more holes. I mean, if you have more holes in your disk, each hole either gives you a new irreducible affine component in the reduction over the reduction field, or just a puncture, depending on whether the hole is big or small. Can you think whether a big hole gives you a component, small hole? It's the other way around. A small hole always gives you another component in the reduction, and a big hole, just a puncture. It will remove a point on one of those components. We can see this in the annulus example. So let's take our example with an annulus, except we have here on the left-hand side this a field element A, which is not specified, but on the other side the 1, and it has an outer hole, namely everything that is absolute value bigger than 1, and an inner hole, if you view it as an annulus in the projective line, an inner hole, so given by bounded by upper bound, nor absolute value of A. Now, if the absolute value of A is 1, then the reduction is just take modulo pi, and what you get is remove one point in the residue field, namely the origin gets removed, right? Absolute value equals 1. Smaller than 1. Absolute value of x smaller than 1 is just removing the ideal of the local ring, the maximal ideal. So, but if the absolute value of A is smaller than 1, so the whole is even smaller, then what you have this aphenoid algebra construction that went before, and you again get the union of two affine lines over K. The take-home messages. So the stable reduction of a Mumford curve is obtained by gluing affine pieces of P1 over the residue fields, the projective line over the residue fields. And affine pieces are just, just remove finitely many points of this projective line. And these are pieces of the reductions of rational aphenoid domains in the projective line over the big field K. Now, if we look at this example that we had before with our stable curves over the residue field K, small k, which are stable reductions of a Mumford curve. I'll let you look at this for a few seconds. If you know the answer, well, you can either shout or just keep quiet. I will tell you later. Okay. There are hints already in the talk that will allow you to identify, but another combinatorial way of looking at it is by introducing the Breuer-Titz tree TK. Last week we had the Breuer-Titz tree for the p-adics, and for general K, the only thing that's different is the regularity. So it's a regular tree, and the regularity is p to the f plus 1. So each vertex has p to the f plus 1 edges attached to it, f meaning the residue field extension degree. And now each vertex corresponds to a disk where p to the f maximal subdisks are removed, one for each edge, or one for each element of the residue field. And each edge corresponds to an open annulus without k rational points. We've seen this before. And now if you have a subtree, called also T, of this Breuer-Titz tree, then in this tree you have a vertex. This corresponds to a disk where, well, what can you remove? You can remove only the degree of the vertex. So for each edge inside the tree T, you remove maximal subdisks. An example here is where we're interested in this segment between the red and the blue vertices connected by this dashed edge. It lies inside the Breuer-Titz tree. This is depicted by showing that there are paths, infinite paths to points, namely infinity, 1, 0, and the uniformizer pi in this example. And the broken segment corresponds to this annulus that we had before. Remember, do you have a covering? Small disk, corresponding to the blue vertex, here down below. The blue vertex corresponds to the circle with radius pi, absolute value of pi. And the red vertex corresponds to the circle, unit circle, so the radius is 1. And remember that the dashed edge had no points. It was an annulus, an open annulus without any points. So well, there are points, but you don't see them over the field K. So this is the broken edge that corresponds to this open annulus. Now, as I said before, a rigid analytic space is obtained from aphenoid spaces by gluing them. And you could do this by taking coverings of such a rigid analytic space, but you need to have them pure. Pure means that you have two patches and they intersect. So you want affine things to be corresponding. So there is an affine Z in the reduction of U, such that upstairs, the intersection of the two patches is the inverse image of this affine piece Z with respect to the reduction map of patch U. So this is the technical part, but the important part is if two patches intersect, then you have two reductions, one reduction to the intersection and one reduction, so there's a big bar here over the intersection, mapping to U bar, coming from the inclusion map, and this has to be injective. Now, the thing is, it's not always injective. So in this example, you have U0, a disk, and U1, an annulus. So this time we have this row 0 and row 1. They might be different in their absolute values, but they're ordered in this way here. And you could cover the union with U0 and U1. And this covering is pure if and only if the absolute values of row 1 and row 0 coincide. This is just an annulus case that we've seen. Well, let's look at the case when they do not coincide, when row 1 is actually smaller than actually an open and a closed annulus with something in between.
Patrick, I can hear you.
Cannot hear me? How do I make this?
Patrick, can you hear me?
I can hear you, yes. I'm trying
But
to get out of the
it is very difficult to hear you.
Okay. Do you hear me now?
Yes, but the volume is very low.
Okay, I'll try to. How do I get out of the full screen mode? I say stop share.
Okay.
I'll make it myself louder and then I'll share again.
Yes.
Can you hear me?
Yes, now it's better. The sound is better now.
Share. Can you? So.
Do you have problems?
Okay. Yeah, here we are.
Now we can see your presentation. Go ahead.
Okay, so we have in this example U0 and U1. U0 is a disk and U1 is an annulus. And they intersect each other because the row 0 and the row 1 are ordered in this way here. And the covering is just given by U0 and U1. And this is pure if and only if row 1 and row 0 have the same absolute value. In that case, you just have, I will look at the case when when these are not the same. So row 0 is bigger than row 1. What you then have is an annulus. The intersection is an annulus. If they're the same, then the annulus, if row 0 and row 1 are the same, then the intersection is an annulus of thickness 0. But if they're not the same, then you have real thickness, and then the reduction map is a cross. Two affine lines over the residue field intersecting. But U0, the reduction of U0 is just an affine line, which is it's a disk. The reduction then will be an affine line, and then the induced map between these reductions intersection to U0 cannot be injective in this case. So you have to be careful how you arrange your hold disks if you want to make a pure aphenoid covering, and that's what you need in order to get stable curves. Namely, the intersection graph of a stable curve can be given as the irreducible components are the vertices and the double points are the edges. Here are the intersection graphs of our genus 2 example that we had before. Okay, here remember, here we were this picture, this irreducible curve drawn as a circle with genus 2 will be just one component, so one vertex, number 2. And then here you have two components of two genus 1 curves intersecting in one point, so one edge. So can you tell us or see which of those graphs belong to Mumford curves? We have to understand the relationship between the topology of those graphs and the genus of the curve. So first of all, given a pure aphenoid covering of a Mumford curve, one can make a reduction curve with respect to this covering by gluing the reductions of the patches of U along the reductions of the intersections. The gluing works because it's a pure covering. The intersections are always injectively inside the reductions of the patches. So you can glue this together nicely, and what you get is a semi-stable curve over the reduction field K, small k, of the residue field K. This is a singular projective curve called XU bar, and all irreducible components of the singular curve are rational curves, projective lines, and the singular points are just ordinary double points. And then you can define what is the reduction graph of this of the Mumford curve X with respect to this covering U is just the intersection graph of this stable curve. So here are answers. Which stable reductions belong to Mumford curves? Remember, genus is always 2 arithmetically, but what you want is irreducible components, which are all rational curves. These are the blue ones, blue circled curves. They have all their irreducible components are rational curves. So these belong to Mumford curves. And in order to understand the other picture, the theorem says by Mumford that the first Betti number of any reduction graph of a Mumford curve of genus G equals to this number G. So remember, we had our semi-stable curve, and you make a reduction graph out of it by the intersection graph, and the first Betti number is the same as the genus of the curve. So if you have a Mumford curve given by a Schottky group in a universal covering omega modulo gamma, then what you can do is take the reduction graph GU, and the universal covering of that as a combinatorial or object is a tree. You can embed this into the Briatitz tree, and in this way you obtain a disjoint covering of the k rational points of the universal covering of the curve by taking for the vertices namely this disks with finitely many subdisks removed, and this quotients out to a cover of the k rational points of the Mumford curve X. We call this covering verticial. Remember, it's a covering, only vertices. Usually I take only vertices because edges also correspond to some space, but they don't have k rational points, these edges, these annuli, open annuli. So you can, from the vertices only, you can make a disjoint covering but only of the k rational points of your Mumford curve X. Now, in order to answer the question again, using the combinatorial data, you just look at those graphs, which are blue. They have, well, you can, if you don't see the numbers, just see the graph. You have 2 loops always. The first Betti number is 2, and that's the genus of our Mumford curve. Of the curve. Genus of the curve is 2, and the first Betti number of the graphs have to be 2. The other graphs, the black ones, forgetting about the numbers, do not have this first Betti number equal 2. I thank you for your patience, and here's my reference, namely the Green Book, Rigid Analytic Geometry and its Applications by Fresnel and van der Put.
Thank you, Patrick. Let me stop recording. Okay, stop recording.